Hi, my name's Steve. I'm doing my final project on insurance costs. So I've got a data set with a dependent variable, which is a cost of private health insurance, and we've got some predictor variables which we'll use to help model the cost of health insurance. So I'll have a quick look at the data set. So here's just a preview of the top 10. So charges here is the cost of insurance. This is our dependent variable. And then we've got the 6 predictor variables. So we've got age, sex or gender. So 0 is female, 1 is male. We've got BMI, body mass index, a continuous variable there. Number of children, smoker, and 0 is no, 1 is yes, and then region, which is goes from 0 to 3. The data is taken from America, so it's 0 is northeast, 1 southeast, 2 southwest, and 3 northwest. So they're the 6 predictor variables that we'll use, and we'll look to build a model using those to predict the charges, the cost of private health insurance. We've just got a quick summary here of those variables. So it looks like the mean is just over 13,000, mean age 39, and so on. So that's the basis of the data set. We've got a few plots here. So it does look like the average cost of insurance does appear to go up as body mass index increases. So there's possibly some relationship there, some correlation. Got here the cost for females on the left and male here. Doesn't look to be significantly different. This one's interesting, the cost by age. What we can see here, it looks like while overall there may not be a significant difference between a younger age and an older age, the minimum insurance definitely increases as age increases. As we can see that this line here is increasing, so the minimum insurance cost is increasing with age. Here we've got cost by number of children, and it does look like the cost is potentially lower for someone with more children, which is interesting. This is what you'd expect. It's much higher for a smoker on the right here than a non-smoker, and again by region there's not all that much difference. So we'll look to potentially plot a linear, or look for a linear regression model for the series. So I'll put this in here, and it looks like a lot of the variables are significant. The only ones that aren't are gender and region, which were the ones we thought didn't look too significant in those initial plots. So that makes sense, and it looks like with the R-squared value of 0.74, it looks like a regression model will be a good fit for this data set. So we'll look to do that using the Bayesian method. Here I've got the JAGS model diagram, and so what we'll do is model all of those variables using a normal distribution. As can be seen here, we've got all of the betas modeled as normal, distributions, a uniform distribution for the variance, and a student t distribution here as well. So that's how we'll model the data set in JAGS. And here is the model string. So the data set here, I've just put in some values for a prediction, but that's not all that important at this stage. And here I've set the model, and I've used uninformative priors for this. I wasn't really able to come up with any expert priors for this data set. There weren't any provided, and I couldn't think of a good way to come up with any expert priors, so I've stuck with normal priors, standardized the data, and then again come out with a prediction at the end, although again not all that important at this stage. But that's the model, the string that I've used in R and in JAGS. So using that model, you get the following diagnostics. So beta 1 here, I mean, they all look fairly similar, but we'll go over them one by one. So beta 1, it's a MCSE of well below 1, so that looks good. And it's the same with most of these other, all of the betas except for beta 5 here is the only one that's got an MCSE above 1. It's also got a lower ESS value than the others, and the shrink factor plot is the only one that doesn't look as good. So there's possibly some autocorrelation or some issues with beta 5, but the others all look good. The shrink factor plot in all of those is fine. MCSE looks good in all of those, and they all look to be mixing. The chains look to have mixed well. So the diagnostics look fairly good here, except for perhaps beta 5. And now we look at the posteriors. So we've got intercept, age, sex, body mass index, number of children, whether they're a smoker or not, and the region lived in. So it looks like all of them are far from 0 except the BMI at -2. And that does contain 0 in the 95% HDI. But other than that, all the others are far from 0 and don't contain 0 in the 95% interval. So we can say that the others, all of those dependent variables other than the BMI, are significant in the model. They're a significant part in explaining the change in the cost of insurance, but perhaps not the BMI. And also looking at the R-squared value here, we've got a really good R-squared value of 0.96, which is stating that 96% of the variance of the cost of insurance is described by these 6 predicted variables, which is really a really high R-squared value, which means the model's looking good. So I'll continue to work on that for the report, but that's what I've got so far. Thank you.